Good afternoon, ladies and gentlemen, boys and girls, and everybody else. Welcome to another scintillating episode of Mr. Smith Talks About Calculus. From my Dodgers garb, you can tell that yes, we are still in the World Series, and I'm wearing my one of three actually. Good luck, Dodgers, Ren Spooner, classic T-shirt or classic shirts. Hoping that tonight in Game 6 we are successful in bringing home the first World Series title to the city of Los Angeles in 32 long years. Be nice. And if we are successful tomorrow, you will see a very happy man on the screen. Anywho, we're just charging right through chapter 3, and this is where some just really fantastically fun stuff starts to happen, specifically as it relates to the derivative of a function and the actual curve that that function makes, and the way that we can use information from the derivative to glean information about what the curve of our function looks like, which is a really powerful thing to be able to do, particularly in the pre-graphing utility days, when you didn't have one of these guys to just tell you exactly what a function looked like. We kind of take this for granted now. The first and second derivative of a function were remarkably useful tools in figuring out what curves look like, and not just doing the biggest XY table of all time, but having some intuition as to what the important points on a curve were and where things are changing and things are staying the same. The first and then the second derivative are going to give us the keys to that kingdom in terms of being able to construct some pretty accurate graphs, kind of graduating from our Algebra 2 pre-calc, kind of just guessing in between our x-intercepts. Now with calculus, we're going to be able to look at specific turning points, something called concavity, which we'll see in our next section. And so the intermarriage of the derivative and the curve of a function is sort of just a fundamentally important concept in your first year of calculus, and it will show up a lot on your AP test. And so we're going to go through some, like a lot of stuff in calculus, the way that it's presented. I'm still wrapping my head around the best way to present this stuff. It starts out kind of dry, like, oh, here's definition, but we need big picture here of the derivative is telling us important things about how quantities change, and the graph of a function is the picture of that change. And so using the derivative to figure out what a graph looks like just makes sense. It's the language that we can use to describe that picture, even if we don't know what the picture looks like at first. The derivative gives us some key points to kind of start our painting, as it were. Okay. So with all of that said, we are going to jump into 3.4, which is called is this gonna work? Oh, there's my wrist. Cool. Maybe. Is called 3.4. Increasing and decreasing functions and first derivative test. And you will see that I have pre-prepared, I guess I don't need two pre's there, I've just prepared with this figure already drawn. I just lifted it as nearly identically as possible from page 236 in your text. So what would be a good idea for you right now is either from the recreation that I made on the page, pause the screen and copy it down on yours, or go into your textbook and do the same. But in any case, press pause on the replay, make sure you have this down, because our first whole discussion of today's lecture is going to be looking at the different parts of this curve and the language that we're going to use to describe certain intervals here. Okay, so quick pause. 5, 4, 3, 2, 1. And welcome back. Okay. If you actually pause, I don't know. If you didn't, that would just look weird. So what we have here is a set of points describing our function f of x, which is sort of incidental here. And we've got a, b, c, d, e, f, and g. In between our x values of x1 and x sub 7. Okay, and so each of these lettered points has an x coordinate and a y coordinate, and that's great. Okay, and we already have some intuition and some understanding of looking at the graph of a function, the curve, talking about certain points when it's increasing and when it's decreasing. And we could, without our formal definition, just kind of trace this out and say, like, okay, what is my pencil doing? Well, I'm increasing, I'm increasing, I'm increasing to B. And now I'm decreasing, I'm decreasing, I'm decreasing, I'm decreasing to C. I'm increasing, I'm increasing, I'm increasing, I'm increasing to D. And I'm decreasing, I'm decreasing, I'm decreasing to E. I'm increasing, I'm increasing, I'm increasing to F. And then, oh, I'm increasing, I keep increasing. So that's kind of a funny one. And it just means that on a given interval, the values are getting bigger, the function values are getting bigger as the x values are getting bigger, okay? And so what we're about to write is just gonna put that into calculus speak, but if something's increasing, the function is increasing as the x values are increasing, or on the other side, if the function is decreasing as the x values are increasing, then you've got a decreasing function on that interval. So we're gonna write down those two definitions, but then make the connection between, okay, why, yeah, okay, increase and decrease, and I have eyeballs, I can see that. But then there's a connection here, like a fundamental connection between the derivative and what a function is doing in terms of increasing and decreasing, that is, it's gonna show up like so much in your life, like so much. So starting to think about, okay, what does that have to do with the derivative? Right now, this is just like algebra. But here we go, 3.4.1, definition of an increasing function. Definition of an increasing function. So a function defined on an interval, a function defined on an interval is increasing on that interval no scooch pooch. There we go. There we go. Light on. Looking out. Better one. Better two. Better one. No, better one. If and only if. Ooh, that's a good one. Goes both ways. Goes both ways. If and only if, or if, you can write it as IFF. If f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2. As you move from the left up to the right on the x-axis, the function values get bigger. Okay? So the bigger x value leads to the bigger function value. That makes sense. Where x sub 1 and x sub 2 are any numbers in the interval, or on the interval. All right, cool, cool. Yeah, you move to the right, it goes up. It's not complicated. So from our figure 1, if we were to, pull out the intervals on which our function f is increasing, it's what I just said. When you move from left to right, the curve goes up. So from figure 1, let's pull out those intervals. As we move left to right, from A to B is going up. So the first interval would be between x sub 1 and x sub 2. All right, cool, cool. Not there. Now as we move right, it's dropping. But then from C to D, represented by the interval x sub 3 to x sub 4, we are increasing. We are increasing. Cool. How about from D to E? Nah. We are dropping, decreasing. From E to F, yeah, another increasing, which is x sub 5 to x. Well, actually, let's pump the brakes here, because we can actually get 2 for the price of 1. Yeah, it's increasing from x sub 5 to x sub 6, but then it actually keeps going. Okay, so from x sub 5 all the way to x sub 7, and from the way that that's kind of drawn, it seems like it will be forever, but who knows what it's going to do outside of this bigger interval. Cool. So then 3.4.2 is the definition, definition of a decreasing function whose definition goes much the same as this one, but we're just going to flop this inequality. Okay? That as we move to the right with our x values, the function values get smaller. Okay? So a function on an interval, or function defined on an interval, is decreasing on that interval if and only if f of x sub 1 is greater than, oh, that's a trick, greater than f of x sub 2 wherever or whenever x sub 1 is less than x sub 2. Okay? So as we increase our x values, the function values decrease. It gets smaller. Where x sub 1 and x sub 2 are any numbers on that interval. All right, cool. So as you move to the right, the function goes down. Simple. So we're going to pick out those intervals from figure 1 that adhere to that definition. So for figure 1, our decreasing intervals are going to be between B and C. So x sub 2 to x sub 3, x sub 2 to x sub 3, y después from D to E, which is x sub 4 to x sub 5. God bless me. Whew, pardon me. Whew. Smoke in the air. Yeah. Okay. So you're probably thinking, Mr. Smith, did you bring us all the way out here to the YouTube to show us this? Because this does not seem that interesting. Like, we've seen increasing and decreasing, or at least have some sense of what it means. No, is my response. No, that's not the only reason I brought you out here. Okay. This vast tundra. It's because the increasing and decreasing nature of any function for any interval has a direct fundamental relationship to its derivative on that interval. Say again. The increasing or decreasing nature of any function has a direct relationship to the nature of its derivative on that interval. How? Great question. Bust out the straight edge. Go back to figure 1. Pretend this is a surfboard. This green surfboard of destiny represents the derivative. Okay. Well, represents the tangent line to the curve, but we know that that tangent line's slope is the derivative at a specific point. And so let's look at what the nature of this tangent line is at different points on our curve, or different intervals. Well, hopefully remember Algebra 1. This is a positive, 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 and we are increasing, 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 positive, 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 positive. It's kind of slowing down, less positive, but it's still increasing, and then we hit boom, horizontal. Which in 3.1 we said, okay, that's a critical point. There's something happening here when our derivative goes horizontal, or better put, when our tangent goes horizontal and our derivative goes to 0. Because now, as we enter this decreasing interval, look at that fundamental shift. We've gone from a positive slope to our tangent line, a positive derivative, to a negative slope to that tangent line, which indicates a negative derivative. And that negativity of our derivative maintains all throughout this interval until we reach C. And then it goes positive up to D. And then it kind of freaks out at D because it doesn't know what to do. It's like too gnarly of a turn. So we don't actually have a derivative at D. But on the one side, we're definitely positive, and on the other side, we're definitely negative. And the negativity indicates decreasing. And then we turn the corner here at this horizontal tangent, and then we're increasing because we're positive, and then we go to 0. Then here's a twist. It goes straight back to positive. And so we're increasing again. Okay, so we're actually increasing this whole time, just a little bit of a hitch. So what does that surfboard ride have to do with this definition and derivatives? Because the positivity or negativity of your derivative at any given interval tells you whether your function is increasing or decreasing, and that is very important. Okay? Whether your derivative is positive or negative indicates to you what your function is doing in terms of increasing or decreasing. And that can be valuable information if you are trying to put together a picture of this curve. Okay, so there's actually a theorem. It doesn't have a name, which I don't know if that's like a sad thing that we forgot the guy's name who figured this out, or if it's just been, maybe it was just so fundamentally obvious that nobody got to claim it. But you would think the guy who invented calculus, maybe that Newton did, or I don't know, man. I don't know that much math history. It's fascinating though. If you ever have the opportunity to take a math history class in college, I never did, but you should. It's insane the stuff that mathematicians figured out thousands of years ago. Well, Newton was not thousands of years ago, but some of those Greeks, man, figuring out the circumference of the Earth using trig, whew, look it up. I forget the dude's name. Erasthenes? Yeah. Look up Eratosthenes. He'll blow your mind. Anyway, so this is a nameless theorem, which we're going to call 3.4.3. I got to introduce my geometry kids to Pythagoras the other day, whose name we get the Pythagorean theorem. He was a good dude. Rumor has it he was the father-in-law of Milo, the dude who picked up the cow calf every day for his life. And so by the time he was an old man, he could pick up a grown cow. I don't know if that's true, but I heard it, so it might be true. It's on the internet. Most things on the internet are true, right? 3.4.3 theorem. Let the function f be continuous on the closed interval from a to b. So continuous is one condition. Continuous on the closed interval from a to b. And differentiable on the open interval between a and b. Then what I just sort of verbally explained and visually showed with the green surfboard is the following. First, if the derivative of f is greater than 0 for all x in that interval, then f is increasing on that closed interval. We don't really need to get our panties in a bunch about open here and close here. It's just not that important. Maybe I'll change my mind and say differently later, but for now, don't fret too much about that. And then the second thing is that if f prime of x is less than 0 for all x in that open interval, then f is decreasing on that closed interval. So again, the value of our derivative tells us what our function is doing in terms of increasing and decreasing. And that can be a very important thing. And it's a positive derivative, it's a positive tangent line, and so we are increasing. If it's a negative derivative, then it's a negative tangent line or slope to our tangent line, and we're decreasing. Okay? So we can put this to immediate use. If you have your graphing utility, let's bust that out. So basically what's going to happen here is we're just going to do a quick illustration of this, and we're going to compare the graph of a function to the graph of its derivative and see if this actually holds up. Okay, because it's one thing to write it down and believe it, but let's see it. Okay, so illustration 1. Let's say we had f of x equal to x cubed minus 3x squared. X cubed minus 3x squared. Nice little cubic function. So let's see what our graphing calculator says. Ooh, I was having some fun with my Algebra 2 financial kids today, and we discovered E together, which actually got us to be able to look at some calculus, because the natural number E is defined as the limit of this expression as x goes to infinity, which is kind of cool. And so the graph, you can see, is kind of approaching this flat line, which is number e. It's good stuff. But we're not doing that today. We're doing, what are we doing? We're doing the first derivative test. Well, not yet. We're doing increasing and decreasing. So x cubed minus 3x squared. And then window, oh, I don't know. Let's just do like a kind of normal one. -5 to 5. Like -5 to 5 and see how that goes. And then maybe we'll change it up if it sucks. But you just got to try and then see what happens. Spinning, 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 spinning. Oh, 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 oh. Yeah, that was tight. That was a perfect window. Okay. Because now we see, you might think, well, what if more stuff happens over here, Mr. Smith? Well, calm yourselves. We all took Algebra 2. We know that a cubic function has a Travolta shape to it. And we can see both arms of the Travolta here. There's nothing else going on here. This just plunges down to infinity. This just plunges up to positive infinity. It's not plunging. Soars up to positive infinity. Travolta. So this is going to be good. So based on what I said and what you wrote, we can kind of do a quick analysis of this graph that, okay, it's increasing from like all the way over there, like just negative infinity. It's just like forever, just increasing, increasing, increasing until it gets to this action spot. And at 0, it looks like it decides, I don't really like being positive. Let's go through like some turbulent 20s and just, I'm negative. I'm a teenager. I'm angsty. And we're decreasing until like there. And then it like kind of hits rock bottom. And I'm like, no, only way up is up. And turns around and is positive the rest of the way. So what we should expect is that if we are to plot the derivative graph, which we will in just a second. Oh, don't go away on me. The places on our function where we are increasing, according to the theorem we just wrote down, our derivative is positive, which means it needs to be above the x-axis. So for like all of this area, we're going to have a positive derivative above the x-axis. Here to here, when we're decreasing, it's going to dip underneath the x-axis and be negative that whole time. And then as soon as this guy turns around, it's going to cross back over the x-axis and have a positive value for the rest of time. Okay, so let's see if that bears out. So there's our function, which means the derivative of f is 3x squared minus 6x. So 3x squared minus 6x will go into our graph. 3x squared minus 6x. Nope. Let's see what happens. Graph. Whoa, whoa, whoa. Is that what we expected? Let's see. So, I'm gonna zoom in here a little bit. Oh yeah, zoom in. Okay. So the red parabola is our derivative. And what we said needed to be displayed is that for all of our increasing values on our blue curve, our derivative needs to be positive. And from 0 all the way back towards negative infinity, we can see that this red curve is positive. Okay? These are all positive numbers. As soon as our blue function turns around and starts decreasing, that derivative crosses the x-axis and has negative values. Okay? Has negative values. So all of these values between 0 and 2 correspond to negative slopes of our tangent as we're traversing this section between, as we're traversing that section between 0 and 2. But then as soon as our tangent decides to stop the pity party, stop being so negative, and turns around, at that exact moment that the derivative goes from 0 here to just slightly positive, the graph of our derivative reflects that, and we now have positive values above the x-axis for all time as we travolta our way to glory. Okay. This, and we'll come back to this in later sections, but feeling out characteristics of our graph based on our derivative or vice versa is like sort of like this really Jedi level deep comprehension of calculus that we're all going to attain to. Okay, we might all be Padawans right now, but eventually we're going to be able to like, oh yeah, this like interplay between derivative and function, or even second derivative. That's where the good stuff happens. That's where you kind of spread your wings and show a deeper conceptual understanding of what's going on, more than just, I can compute derivative. Like, that's the baseline. I expect you to be able to compute derivatives. Power rule, whatever, we don't care, that's easy. It's this interplay that we're gonna really kind of earn our stripes, as it were, if we were in a Kellogg commercial. They're great. They really are, Tony. They really are. You guys probably don't even know what I'm talking about, because I don't even know if they even do cereal commercials anymore. Tony the Tiger, Frosted Flakes. I'm a dinosaur. I'm sorry. Can't help it. Okay. Kind of the takeaway from this problem is when the graph of f prime of x is above the x-axis, f of x was increasing. And the flip side is that when the graph of the derivative is below the x-axis, the opposite is happening. Your function is decreasing. The curve is going down. Okay. All right, so that was like, I don't want to oversimplify this, but I also don't want to overcomplicate this, okay? But this interplay between the derivative and the function, I don't know, don't take it for granted, but don't let it spook you out too bad either. The more we see this, the more it'll kind of be like, yeah, okay, yeah, sure, makes sense, hopefully. Okay, so there's like the first half of that title, increasing and decreasing functions. But now we get to the second part, okay? The first derivative test. And to be honest, this is kind of like the main course, you know? Main course is the first derivative test. Because the first derivative test, I mean, it's going to include what we just did with increasing and decreasing, to be sure. But now we're going to have this tool that enables us to put to use the relative extrema idea that we saw in 3.1. Like, okay, when our derivative is 0 or DNE, there's something going on here. But how do we know for sure what's going on? The first derivative test is how we know for sure. By looking at what's happening on either side of those critical points, either the horizontal derivative or the non-existent derivative because it's too gnarly or whatever, we're going to be able to make an actual intelligent statement about what kind of extrema, if any, exists at those critical points. So we're not just kind of flapping in the wind guessing. The first derivative test is the tool that allows us to do that. So, backside. Let's do it. I think I'm just going to give you the theorem and we're going to just play with it. Yeah, why not? I don't know. Nobody's here to tell me otherwise because I'm sitting in an empty room. So yeah. The first derivative test for relative extrema is the 3.4.4 theorem. Let me just tell you what it says before we write it down. Yeah. Let's tell you what it says so that this isn't just like some slog writing down some theorem. First derivative test, again, is kind of intuitive and sort of makes sense. When we get to critical points on a curve, critical either because they have a horizontal tangent or no tangent, in order to determine if the critical point is also the location of a relative extrema, meaning a relative max or a relative min, we can use the first derivative to our advantage. Because, whoa, almost spilled my coffee. That's very not warm, but still would have been a bummer. Because consider B. Just looking at B, that is a relative maximum. It just is. Okay. Everything to the left is smaller, everything to the right is smaller. Okay. Here, as we approach B, our derivative is positive. Positive, zero. Zero tells us that that's a critical point. Immediately after that critical point, remember we were positive, zero. Immediately after that critical point of zero, it goes negative. Positive, negative, positive, negative. That change in the sign of our derivative, of our slope to our tangent line, indicates that a extrema exists there. In this case, from positive to negative says, oh, there's a maximum there. Let's check out C. We're going negative, 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 zero. So this could be a relative extrema because it's a critical point. We've gone from negative and then immediately afterwards, positive. Negative, positive, negative, positive. We've again switched signs. This time from negative to a positive, indicating the existence of a relative minimum. Very kind of intuitive, okay? Positive to negative. There's a change in what our derivative is doing. Thus, based on what we just wrote, there is a change in what our function is doing from either increasing to decreasing or decreasing to increasing. That is the connection here. That is why we just wrote this down. Because if your derivative changes signs, the nature of your function and thus the nature of your curve changes its character. And that's not quite what I want to say. It changes. In this case, positive derivative to negative derivative says that's a max and that's a min. But what if we don't have a derivative? Like at D, does it still work? This is the too gnarly. You're just like freaking out. It's like a glitch in the matrix. I don't know where the derivative goes. But what I do know is to the left of this point, we are just positive, 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 positive. And then immediately to the right, we are negative. And clearly that's a relative max, okay? All around it, everything is smaller than that. Cool. So you don't actually need the derivative to exist to have a relative extrema, which we saw in 3.1, but now we have the tool to talk about it. E follows the negative to the positive, so it's a minimum. And then here's the case that we're always on the lookout for with the first derivative test. We're positive, we're positive, we're positive, we're positive, we're positive, we're positive, and then we're zero. We've hit a horizontal tangent. And this is why a horizontal tangent is not the test to figure out relative maxes and mins, because it is not sufficient to conclude that just because you have a horizontal tangent, you have a relative extrema, illustrated by this point right here. We've hit a horizontal tangent. We have hit the derivative equal to zero, but it doesn't change, it being the derivative, doesn't change signs. It goes from positive and kind of pauses at zero, but then it continues to be positive. It just like stops for a second. And because of that, this is not a relative extrema, okay? On either side, you have numbers both bigger and smaller than f. not a relative extrema. Okay? And so the first derivative test is simply the test that we will apply to critical points and figure out what's going on either side of that point with our derivative. And what's going on will indicate whether we have an extrema and what type we have. Okay? So maybe rewind a little bit and just go through that again, kind of get that intuitive sense of what the first derivative test is going to tell us, because we're about to hit you with the definition, and sometimes that just overwhelms us a little bit. Maybe just press pause, take a deep breath, go for a walk, and we're back. Okay. Whew. I have my watch on, so I have no idea how long this is taking, and I don't, yeah, so it could be 7 o'clock at night right now. All right, that's a lie, because the bell hasn't rung while I was out of school, but I feel like this is taking a while. So 3.4.4, but it's okay. This is like a very, 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 I say very, very important section. So we're gonna take our time. What is it? Be quick, but don't hurry. Yeah, that's what we're doing. 3.4.4. The first derivative test for relative extrema, which is just going to kind of translate what we just walked through into black and white rules that we can rely on. The first derivative test for relative extrema. So let the function f be continuous. At all points of the open interval hello, the party. The open interval between a and b containing the number c except possibly sorry, never, that doesn't come later. It has to be defined at those points, because if it doesn't exist there, it can't be a relative extrema, because that doesn't even make sense. Yeah, you got to have the value there. So the except possibly at C is for the derivative. Good catch, whoever just pointed that out. Okay. Containing the number C, and suppose that the derivative of f or f prime, suppose that f prime exists at all numbers in A to B, and then this is where we can say except possibly at C itself. Which is to say, in order to use the first derivative test, we need the promise of continuity on the entirety of the interval. Okay, there can't be any holes, because what if one of those holes is at the place where the extrema should be? So you have to have the promise of continuity. You do not need the promise of continuity on the entire interval, because it's okay if we're not differentiable at this number C, which we're going to see as the critical number. And that's exactly the case for point D here. Okay, if we were to look at the interval from C to F, for example, it's continuous everywhere. There's no holes here, but it's not differentiable at D. And yet there is still the ability to apply the first derivative test here, which we'll see in a second. Okay, so we don't need to be differentiable everywhere, but we do need to be continuous. Then, if So first we'll do little guy, y. If f prime of x, the derivative of x of f is greater than 0 for all values of x, in some interval some open interval having c as a right endpoint, okay, so think about that. So we're on some interval and our derivative is positive until c being the right endpoint, so it's positive all the way to c. And if the derivative of f is less than 0 for all values of x in some open interval having c as its left endpoint, then f has a relative maximum. At c. Okay, so if we're increasing until c, and then all of a sudden we're decreasing after c, we're increasing and then we're decreasing, that describes the location of a maximum. So that would be point B here. Some open interval containing x sub 2, we're increasing all the way. Our derivative is positive that whole time. But then on an interval that has x sub 2 as its left endpoint, we're less than 0 for our derivative the whole way. And thus B is a relative max. Okay. The second part is just the reverse. That if we are negative on some interval to c, and then suddenly positive after c, that's going to be a relative minimum. Okay, so it's going to sound much similar. Just going to switch that around a little bit. So the second condition, or the second case, is if the derivative of f is less than 0, so we are a decreasing function for all values of x in some open interval having c as a right endpoint, and if the derivative of x then suddenly goes positive after that, so f prime of x is greater than 0 for all values of x in some open interval having c as its left endpoint, then f has a relative minimum at c. Okay, that was like a whole deal. A lot of writing. That was I feel like let's see if we can just translate this. Let's just see, well, Mr. Smith, what is the first derivative test? Like what are we doing here? Just tell me, bro. A, not your bro, I'm your teacher. B, what we're doing here is the first derivative test. And what all this says is if we can find the critical points of a function and just see, hey, is there a change in the value of our derivative on either side, then you have identified a relative extrema. Okay, this gives it to you more specifically. It tells you based on what that change is, whether it's maximum or minimum. And yes, you could commit this to memory and like, yeah, like, oh yeah, it went from negative to positive, then that means it's a minimum. Oh, it went to positive, negative. But I think a better thing to do is just intuitively think about what the derivative is telling you. And as you walk through problems like this and you get to a critical point, don't like memorize the thing. Just think, oh, okay, well, on the one side it's positive, and on the one side it's negative, so that should be a max. Just think these things through. The less random access memory in your brain that you commit to like memorizing stuff, probably the better off you are. You can get some like deep understanding going on, and then you can just like get like the trig functions in your RAM. Okay, that's like the stuff you got to memorize because that's not really intuitive unless you memorize those proofs. Okay, but stuff like this, just think about what the derivative is and figure it out as you go. Okay, so here's the first derivative test for dummies. Or let's say finding relative extrema for dummies. I don't mean that in a derogatory way. There was a very famous, it probably still exists, series of books called Some Topic for Dummies that just kind of parsed it down, distilled down a topic to something that a dummy could understand, or just somebody who's not an expert could pick up the book and say, oh, okay, I kind of get it now. So let's do that for the first derivative test, which allows us to find relative extrema for dummies via the first derivative test. So step one, compute the derivative of f. That's a good place to start. It's all based on the derivative. You should probably figure out what the derivative is. 2, determine critical numbers which means where f prime of x equals 0 or f prime of x dne. And then your book just says apply first derivative test, which, okay, that's what you're going to do. But we're going to just parse, we're going to tease that out a little bit for step 3. Does f prime of x change on one side of a critical number to the other? No. Then not an extrema. Sorry, bro. Yes. Here's kind of like the flow chart in your brain, maybe. Okay, does it change? No, you're done. Not an extrema. Yes. Follow-up question, what kind of change? Oh, well, it went from a positive derivative to a negative. Positive, increasing to negative, decreasing. And that's where that sort of connection between the derivative and the nature of your function is so important, because it's one thing to say that the derivative is positive, but it's another to just understand on that intuitive level that means that your function is increasing. And if you're increasing and then suddenly you're decreasing, that must be a maximum. And the other option is to go from negative, which means you're decreasing, to positive, increasing. Once again, understanding that the negative derivative means that the function is decreasing, and then as soon as you turn the corner, you're positive, which means that there's got to be a relative minimum in between those two things. Oh, excuse me. That means minimum. So there's kind of like the flow, okay? Not progressive, but flow, calculus flow. Oh man, we've been doing this an hour. You know what's going on? Time flies when you're having fun. Okay, well, before we give up on this, we gotta at least do a couple of examples to see how this goes. Are we just gonna power through this whole thing? We'll see. We'll see. Coffee is, the well has run dry. Has it? There's like one more sip left. That's gonna be brutal. It's gonna be so not warm. All right. Let's see if that does the trick. That was not very good. I don't think we're gonna have room here, so we're gonna flip to a new page and do example 1. Ejemplo número 1. So the book has us like plot first, but to me the whole point of the first derivative test is, hey, I don't have a graphing calculator and I want to make some like intelligent comments about what the curve looks like. So we're not going to do that. We'll use it at the end to kind of confirm our findings, but we're going to do this. We're going to do this the hard way. Hello, class. How are we? Sweeney, the flow is on point. Mr. Schwartzberg, 5th period, topics and calculus. I think they're topics and calculus. Topics and calculus course. Just walked by. Walking the wrong way, I might add. Upstream, against the arrows. I thought that was just Miss Coghill's class that did that, but apparently even mathematicians can't follow simple directions. Not just English students. And I know that those groups are not mutually exclusive, but that's okay. Example 1, f of x is equal to x cubed minus 6x squared plus 9x plus 1. Okay, so just like our first quick analysis, this is a cubic. It's got a positive leading coefficient. We're Travolta all day, okay? We know that. The big picture is not in question. It's the little details that we're interested in, okay? Where are those turning points that we know are there, okay? Where before we were always kind of just guessing, we could find the x-intercepts and the y-intercepts, and kind of get, I guess not y-intercepts or aren't a function, the y-intercept, excuse me. And that will give you kind of an idea. But do you remember from algebra 2 or whatever, whenever you learn this, you would have a cubic and you're like, oh, here's the 3 roots. Oh, I know this is the end behavior. Oh, I know that this is the y-intercept. And then you're just like, oh, I'm just going to guess that it looks like this. Ta-da! But really, you had no stinking idea where this turning point was. Or even this one. You're just kind of like, eh, hope so. Well, now we're going to be like a little bit savvier, a little bit more calculus-y, a year older, maybe 2 years older, I don't know. And we're going to apply calculus to figure out where the heck is this? Because now we know that these points where we got the relative extrema, where we have these turning points, happen at critical points when our derivative is 0. Okay, that was a big lead up. First thing we're gonna do, step 1. Compute the derivative. F primo de x. Yes, F primo de x. I don't know if it's primo. F prime is going to be 3x squared minus 12x plus 9. Okay. So second thing, according to our finding extrema for dummies, is determine the critical points. Well, we ask ourselves, I think the first thing with critical points is, where are the DNEs? Because that's often kind of forgotten. So if we start there, maybe we won't forget it. So where are the DNEs for 3x squared minus 12x plus 9? Trick question. It's polynomial. There are no DNEs. It exists for all values of x. It is continuous, never has any holes. Okay? So for critical points, only looking for f prime of x equals 0, because f prime of x exists for all x. Which means we're going to set this bad boy equal to 0. That feels like a 3 probably factors out of there. So x squared minus 4x plus 3. Oh, happy day. So x minus 3, x minus 1. Our critical points are x equals 3 and x equals 1. Q. Q, Q, Q. Now what? Well, now what? Step 3 says, well, we said a lot of stuff in step 3, but basically it says first derivative test, okay? Which for our purposes, we're going to do a little chart, okay? Charts are generally pretty useful things. How do we want to do this? Do you want to do this horizontally or vertically? We'll do both. Why not? Overkill? Probably. How does the book do it? The book does it vertically. I kind of like going horizontal. It kind of tells you like what's going on. We'll do both ways. Sure. Okay, so this is kind of gonna like bring back memories of like the TSVA charts from rectilinear motion, where we like have these critical points where the particle stopped. It's kind of like, well, that's exactly what's going on here actually, because the particle stopped when the derivative was equal to 0, when the velocity was equal to 0. We are interested in those same points when our velocity or our derivative is 0, or doesn't exist, but it exists everywhere. So kind of just like off to the side, because we're going to do kind of a beefier chart, but kind of what we can picture going on here, if we're starting to get a picture of what this graph looks like, is we've got some intervals that are sort of forced on us by these critical points. So from like negative infinity to 1. When x is equal to 1, we know something fun happens, namely that our derivative is 0. Between 1 and 3, something happens. And at x equals 3, we have another 0 derivative. And for x greater than 3, more stuff happens. So like this is kind of just be like a quick and dirty like pass of seeing what is our derivative doing and what does that mean our curve is doing. Okay, so let's pick a number that's less than 1. I don't know, 0. Plug it into our derivative, we get a positive derivative for any number less than 1. So that tells us, okay, we're increasing towards 1, then we flatline. The first derivative test says if this is going to be a maximum, because we've been increasing all the way to it, we need to see a change in the sign of our derivative directly after it. So we'll pick a value in between 1 and 3, I don't know, 2. Plug that into our derivative. 2 squared is 4, 3 times 4 is 12. Minus 12 times 2 is negative 12, plus 9 is negative 3. Oh, we're in business. We've changed signs. This is an extrema. Specifically, we've gone from increasing to decreasing. It must be a maximum. Then we're decreasing on this interval till we hit the other horizontal tangent. And then the same question. Is this an extrema? Well, in order for it to be an extrema, in this case it will be a minimum, we need to see a change from a negative to a positive. So picking a number in this interval, let's say 4. 4 squared is 16, times 3 is 48, minus 12 times 4 is another 48. That zeroes out, plus 9, positive. Okay. So kind of like the very rough ghost version of this curve is from negative infinity, and this is why the horizontal is kind of nice, because you can kind of sketch it underneath. We're increasing, we're increasing, we're increasing, we're increasing. We hit 1, we get a maximum. We're decreasing, we're decreasing. Oh, I guess we decrease more. We hit 3, and then we're increasing. Okay, so we got a little whoop-de-whoop. Cool, 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 cool. Okay, now if we want to be a little more thorough with that, now that I've done that, we're probably not going to do it like this again, so sorry about that. I think we're going to use the vertical charts. But never say never. Okay? Never say no. No. Did it mute? I thought I muted it. That was weird. It said mute. Can you hear me? Oh, this is going to be bad if I'm muted for the last. How do I even test this? I hope it's not muted. Okay, here we go. Oh, that would be such a bummer. Okay, so like the more bulky version of this is we'll do like an interval column. We'll do the value of f of x, because if we were to actually plot this, and I think we will, I think that will probably be where we leave off today, is we're just going to use this and we're going to make like, yeah, this is what the plot looks like. Oh, but then we'll have to do the cubic. Maybe we won't do that. To be determined. Okay. So f of x, what the value is there. F prime of x equal to like 3 times x minus 3 times x minus 1, which will help us with the positivity and negativity. And our conclusion. What can we say about our curve here? Okay, so the intervals we care about are x is less than 1, x is equal to 1, x is between 1 and 3, x is equal to 3, and x is greater than 3. Okay, just kind of transposing from up here. At 1, and this is where we could get pretty specific with our graph and able to zoom in on exactly where those turning points are. We know that at 1 we have 0 for our derivative, and so too at 3. And we already kind of did this work. We knew that the derivative was increasing as we approached 1 from the left, and then immediately decreasing. Okay, and then on the flip side we had decreasing and then increasing. And so where you would kind of illustrate that you know what this stuff means is you would say, oh, a positive derivative means that f is increasing. And then this 0 point, if we're just taking this in a vacuum and we get to the 0 derivative, we're not really sure until we apply the first derivative test and peek on the other side. and we see, oh, we've gone from f is increasing. Now we have a negative derivative, which indicates that f is decreasing. Now we can intelligently say, okay, now I know what this zero derivative means. It means that f has a relative maximum. Because we have gone from this increasing function to this decreasing function, which was indicated to us by the value of our derivative. The positive derivative said increasing, the negative derivative said decreasing. Furthermore, if we want to get really specific, we can fill in this column and actually say where exactly this minimum is. Not just that it's at 1, but what it is. So if we plug in a 1 to our function, that's why this is f of x, plugging in 1, we get 1 minus 6 is negative 5, plus 9 is positive 4, plus 1 is 5. And so you could get so thorough as to say f has relative max at the point 1, 5. So that if we were going to sit down and plot this entire thing, you could put 1, 5 on the graph and know that that was kind of your turning point there, and not just do the algebra 2 pre-calc guessing game. Like, hope so. No hoping anymore. We're calculus students. There's no hope remaining. Abandon all hope. Oh, I need to get out of here. What time is it? Dag nabbit. I said dag nabbit, it's 2:39, which means I probably need to wait until traffic dies down. Even though with our new hybrid schedule, there really isn't that much parking lot traffic. But, and let's not forget, I don't even have a car, so I'm zipping through there in my bright orange bike. Stay focused, Smith. Let's finish this. Okay. Using the same logic, we've got this decreasing function value indicated by our negative derivative. And then we hit this other point where our derivative indicates a horizontal tangent. But we need to ask ourselves, does this actually tell us that there's a relative extrema here? Well, applying the first derivative test, we've got a negative heading into it from the left. So peeking onto the other side. Oh, now it's positive, which means that f is increasing. This switch from a decreasing function to an increasing function indicates the existence of a minimum at that point. So f has a relative minimum, and just as we did with our maximum, we can get specific, we can get thorough and say that it's at, not just that it's at 3, but list off the actual point by plugging 3 back into our function to figure out the function value at that relative minimum. So 3 cubed is 27, minus 9 times 6, 54, negative 27, sweet, plus 9, plus another 27 is 0. Wow, that was cool. 1. Nice. Sometimes math works. And so it has a relative maximum at 3, 1. First derivative test, kicking butts and taking names. Yeah, this is gonna be a 2-parter. I'm sorry, this is just way too much good stuff for one. But before we call this a day, let's just see if we were to fast forward in time, because in my head we were like in 1723 or something, and we didn't have Texas Instruments. We didn't have Texas. Oh, did we have Texas in 1723? No, we didn't have Texas. I mean, it existed, the land, but we didn't have America. Anyway, fast forwarding from 1723 in the land before America to 2020, when we do have the state of Texas and the company Texas Instruments to give us these wonderful tools of technology. Let's see what this curve looks like. X cubed minus 6x squared plus 9x plus 1. So when we plot this, we're really going to hope that we see a maximum at 1,5 and a minimum at 3,1, and then it just does its normal Travolta thing after that. Oh, let's change the window a little bit, but I'm feeling good. Feeling good about this. Let's maybe turn off the light here. Yeah, do a zoom action. Yeah. Okay. Change the window slightly. Don't need so much X. It's like -1 to. Let's do like 8. I don't know. -1 to like 10. Okay. Oh, it's beauteous. It's beauteous. So now we're not guessing where the humps are. We have figured them out, and we're going to verify relative min. Why is it being? Okay, well, it's for some reason it's not wanting us to get to 3, but hopefully you can agree that that's going to be 3,1, the minimum. Y después el máximo vive a 1.5. That's super weird. I guess we could actually use, let's use second calculate minimum, or this can be a maximum. Left bound, right bound, guess, sure. That's disconcerting, but close enough to 1, and it's definitely 5, okay? Now we can do that same technology, trace, with our minimum. Ask you for a left bound, ask you for a right bound, and then I guess. There you go, 3,1. There must be some way that they are calculating the minimum that's an approximation, which is why we're seeing that 3.000002. But hopefully you are sufficiently placated that our calculus is true. If calculus isn't true, it's just like, what are we doing here? I don't know. Okay, I think the bell's about to ring, which means I need to go home. But we will conclude this because there's still a little more juice here to be squeezed out of this fruit, proverbially speaking, of 3.4. So we'll be back tomorrow. Hopefully I'll be wearing, I'm just gonna let it out of the bag. If the Dodgers win tonight, I'm gonna wear my Christmas Dodgers shirt to school tomorrow because it's gonna be like Christmas in October for Mr. Smith. Yes, I have a Dodgers Hawaiian shirt. That's Christmas. I'm a weird guy, Okay, how do I stop? How do I stop? How do I stop?